Swayam Prabha. Digital India. Educated India.
Hello and welcome to week 6 of the course. So this week we are going to wind up MDP planning. Okay, something we've been doing for the last couple of weeks. This is week 3 of MDPs, and it will be our concluding lecture on MDP planning. So before going into this week's lecture, let's just recap what we've done with MDPs. So in weeks 4 and 5, right, here's all what we did. We defined MDPs. You can see the picture here, policies, value functions, and defined the MDP planning problem. So an MDP is an abstraction of sequential decision making. What we would like to compute for an MDP is optimal behavior, okay, which is encoded as a policy. And a very natural quantity that comes along with the policy is its value function. And we know how to find a value function. You use Bellman's equations and solve them. We know there is an optimal policy, and the problem that we want to solve is that of computing an optimal policy. There are minor variations on this theme. Okay, exactly how you define an MDP, the reward structure, etc. There is some scope for alternative formulations. But then we got a little bit then familiar with ways to solve a given MDP, find an optimal policy. So the basic tools we used for doing that were Banach's fixed point theorem, which goes hand in hand with the Bellman optimality operator. Okay, and this formed the basis for solutions that would go through value iteration. That's one big family of algorithms for MDP planning. And the other one was linear programming, okay, which has an independent existence, but then we can piggyback on that by casting MDP planning as a linear programming problem and solve it. So this is where we left off last week. So the big topic for today is a third family of algorithms for MDP planning called policy iteration. Okay, so we will get started with policy iteration. Curiously, the first step in policy iteration is what's called policy evaluation, okay, which we already saw in week 4. But thereafter, the essence of policy iteration is captured through what is called the policy improvement theorem. Okay, so we will visit the policy improvement theorem, and that will finally put to rest many of the claims that we have made without proofs. Right, the very fact that there is an optimal policy for a given MDP will be a corollary of the policy improvement theorem. Okay, which we will specify and prove, and part of the discussion, right, the discourse today will also be applying the policy improvement theorem into a family of algorithms, which is what is called policy iteration. Okay, so we will also look at policy iteration as a family of algorithms, and in section 3, I will actually go over some existing results on the complexity of policy iteration. Okay, in addition to complexity results for value iteration and linear programming. And with that, we will finish. All right. Okay, so let's get started then with policy iteration by first looking at policy evaluation. Okay, this is something we already did, but just to refresh you. So if you have an MDP and you're given a policy pi, then we know that it has a value function, which is its expected long-term reward starting at each state. Similarly, an action value function, which considers what happens when you take one action and then follow that policy. And we know that the value function is the solution of Bellman's equations, okay, which are a system of linear equations, n equations in n unknowns, right? Those unknowns are the values of each state under this policy. And once you have V pi, you can also get Q pi by just multiplying out and adding rewards, etc. Okay, all right. So the bottom line is, once you are given pi, you can get V pi and Q pi relatively easily. Okay, so you can solve linear equations in cubic time, maybe even less, and then you can get Q pi in n squared k time. Right, if you have n states in k action. So essentially in polynomial in n and k, you can get v pi and q pi. Okay, by that I mean the number of arithmetic operations that you have to perform. All right, okay, so that's policy evaluation. Now we come to the crucial element, right, the core of the policy iteration algorithm, which is a step called policy improvement. Okay, and this is best done by looking at an example. So what I have shown you here on this slide is a policy pi. It's defined on an MDP that has 8 states, S1 through S8, and 4 actions. Okay, the actions are red, blue, black, and green. Okay, so if I'm sort of drawing a picture like this, what it means is this particular policy is taking action red in S1, blue in S2, red in S3, red in S4, black in S5, etc. Okay, that's the policy. Now, I'm going to do something with this policy. Okay, for every state, I'm going to look at every other action. Okay, other being other to the action taken by the policy. Okay, so for example, red is what is being taken at S1 by pi. So we're going to look at green, black, and blue. All right, and each of these actions I'm either going to draw above the line on which I have drawn pi or below. Okay, so green I'm putting above, black and blue I'm putting below. Similar thing for all the other states. On what basis am I doing this? On what basis am I putting actions above and below? On the following. Okay, so the reason I put, let's say, blue below red at S3 is because of the fact that it so happened, let us say, that for this policy, when I calculated q pi of S3 and blue, okay, that was no greater than q pi of S3 and red. Okay, so note that q pi of S3 and red is the same as v pi of S3, right? And similarly, in the other direction, I put black on top of the line in state S7 because q pi of S7 black was strictly greater than q pi of S7 blue. Okay, so also note this convention, you put something above when there is strict greater than in terms of the q values and below when it is less than or equal to. Okay, so equal to will also go below. Okay, and similarly I've applied the same principle, right, for putting all the other actions above or below the line in the corresponding state. Okay, now it turns out that every state which has at least one action that is drawn above the line, we're going to call such states improvable states. Okay, so you can see that there are 5 improvable states, S1, S2, S4, S6, S8. On the other hand, S3, S5, and S8 have all the 3 non-taken actions falling below the line, right? So those are not improvable states. And the actions themselves, right, which we are drawing above the line for each state are called improving actions for that particular state. Okay, so every improvable state has at least one improving action. States that are not improvable, they don't have any improving actions. Okay, now here's what we are going to do. Okay, so suppose we are given pi, we are going to pick one or more improvable states. Okay, so we have some choice in doing this, right? We have 5 improvable states here. We can pick all 5 of them or 2 of them or 3 of them, but we must pick at least one. Okay, and in the improvable states that we have picked, all right, we are going to switch to one of the improving actions. Okay, we have a current action that's being taken, but we are going to let go of that action and switch to one of the improving actions. Okay, and again we might have choice, right? So S2, for example, has 3 improving actions. If we are picking S2 to switch, we can switch to either red, blue, or red, green, or black. Okay, if we do this, let's call the resulting policy pi prime. Okay, so here is one way of going from pi to pi prime. So indeed we have picked S1 and switched from red to green. In S2 we have switched from blue to red. You can see it's red over here. S3 we did not have the option of picking in the first place. Okay, that's because it's not an improvable state. S4, it was an improvable state, but we decided not to pick it. Okay, that's okay. There are some improvable states that you can just leave without switching. But of course, you should at least, for one improvable state, do the switch, right? We've already done that for S1 and S2. S5, again, there's no choice. It's not improvable, so it stays black. S6 and S7 looks like we've done switches. S8 again you cannot. Okay, so note that because of the choice that we have, right, there are multiple possible pi primes that we can get by virtue of following what's written in this box. Okay, it turns out doesn't matter how we are going from pi to pi prime, which pi prime we are going to. This step is called policy improvement. Okay, so there are multiple possible pi prime policies that we can get from pi by doing a step called policy improvement. All right. Okay, so you've heard the word improvable, improving, improvement, right? All forms of that word being used on this slide. We said there are improvable states, improving actions, and this step is called policy improvement. I mean, right now I've just told you, right? It's called this, but why is it called improvable, improving, and improvement? So that is because of the policy improvement theorem. Okay, you'll get the answer to that question on this slide. So let's make things a little bit formal, right? We saw things with the picture on the previous slide. I'm saying basically the same things with notation, right? With an equation over here. So for a given pi, right, we have some fixed policy pi. Let us say that the set of improving actions of pi for a state, okay, is all those actions who have a q value that is higher than v pi of s. Okay, so these were the actions that we drew above the line on the previous slide. Note the strict greater than, and states that have at least one improving action. Okay, those are called improvable states. So the set of all improvable states, let's just define that is of pi. Okay, for pi. So pi has a set of improvable states. Every improvable state will have at least one improving action, maybe more improving action. States which are not improvable, right, will not have any improving actions. Okay, so this is what we defined on the previous slide. And further, right, if pi does have improvable states, right, that means is of pi is not empty, and we obtain pi prime by doing what we called policy improvement, right? So what it basically means is that pi prime is a policy that satisfies that for every state, pi prime of s is either pi of s, okay, and if it is not pi of s, then it is some action that is in the improvable actions of pi of s, of s. Okay, so ia of pi of s is the set of improving actions in of state s, right, according to pi. So pi prime can take an action from that. Okay, so it is either the same as pi of s or it is an improving action. Okay, and additionally, we also want to ensure that pi prime is different from pi, right? If you just take pi itself, it will satisfy that pi of s is always pi of s. It will satisfy the first condition. But we want that pi prime should be different from pi, at least in one state, right? And that must be a state in which pi prime is taking an improving action, right, rather than like a non-improving action. So the second condition is that there exists a state in which pi prime of s is an improving action of pi of s. Okay, so naturally there are multiple possible pi prime that satisfy this. We are okay with any one of them. Okay. Okay, so why is this called policy improvement, and why is this called the policy improvement theorem? Because the following is true. Okay, so the policy improvement theorem states that if pi does not have any improvable states, okay, if is of pi is empty, then pi must be an optimal policy. Okay, so you evaluate a policy, find its v, find its q, and then you compute these two sets, right, ia and is, and you see that there is no improvable state for pi, you can conclude that pi is an optimal policy. On the other hand, if pi does have at least one improvable state, right, then certainly we can do policy improvement on pi, right? At least for that one state, you can pick a different action. If you have multiple improvable states, you can, if you want, pick multiple improving actions and go from pi to pi prime. Doesn't matter how you do this, as long as you do this consistent with the rule that you must switch at least one improvable state to some improving action. All the other states you can either retain or switch to an improving action, right? If you follow that, then the pi prime that you get by doing this, by doing policy improvement, will strictly dominate pi. Okay, so remember our definition: pi prime is greater than pi means value function of pi prime is greater than value function of pi, and that means element wise for every state the value function of pi prime is greater than or equal to the value function of pi, and additionally there is at least one state in which the value function of pi prime is strictly greater than value function of pi. Okay, so there is strict domination that is going on here. Okay, so let me just restate. For a given policy pi, we defined improvable states and improving actions, and defined this operation called policy improvement, which if there is an improvable state, right, one or more improvable states, you can go from pi to pi prime. So what this theorem tells us is, if you don't find any improvable states, you must be at an optimal policy. Okay. On the other hand, if you do find an improvable state, then what can you do, right? You can certainly go to some policy pi prime by doing policy improvement. Lo and behold, pi prime will be a policy that strictly dominates pi. Okay, so this is the policy improvement theorem, and maybe you've already sort of thought about it in the back of your mind, but there is a very natural implication of the policy improvement theorem. Okay, so I've once again written the theorem here for your reference, but what follows from the policy improvement theorem, right? So if pi is a policy that such that it's got an improvable state, right? Then, I'm just restating what's in the theorem, right? Then there exists some pi prime which dominates pi. We know that the set of policies, right, capital pi, is a finite set. Okay, it's got only k to the n policies. Okay, so what's happening is if you pick some pi and it is improvable, you go from pi to some pi prime, right? So maybe from pi prime, again, you evaluate whether it's got improvable states. If it is improvable, again, you'll go to some pi double prime. Notice that by doing this over and over again, you will never come back to pi itself. Okay, so why is that? Because pi prime strictly dominates pi double prime strictly dominates pi prime, etc. So there's no way you can suddenly lose value and come back to pi, right? You'll never visit the same policy twice by just doing this repeatedly. And there is only a finite number of policies. So at some point, right, you need to end up with a policy that does not have any improvable states, right? So there must exist a policy pi star, right, such that the improvable set of pi star is empty, right? And the theorem itself tells us also that if there is such a policy, right, whose improvable set is empty, then that must be an optimal policy. Okay, so the consequence of this is that every MDP must have an optimal policy. Okay, so this is what we claimed earlier. The theorem, right, shows sort of almost constructively how this comes about, right? Because it tells you if you're not at an optimal policy, you just keep improving. Eventually, you have to hit an optimal policy. So the other thing also to connect this up with is the Bellman optimality equations. So with a little bit of working, if you just write things out in full, you will notice that if the set of improvable states of pi star is empty, then V pi star, right, is a fixed point of the Bellman optimality operator. Okay, so which means also it's the solution to the Bellman optimality equations. Okay, so this is again the claim that we had made last time, but modulo the proof of this theorem, right, which is coming up also as a part of this week's lecture. If we take the theorem at face value, right, then what we have is that V pi star, right, satisfies the Bellman optimality equations. We know that the Bellman optimality equations have a unique solution, okay, because of the Banach's fixed point theorem. And therefore, right, if pi star is an optimal policy, then the convention is to denote V pi star as V star, right? Because there might be multiple optimal policies, but all of them have that same unique value function, which can be thought of as the optimal value function for the MDP itself. Okay, all right, good. So we have sort of started on relatively firm footing, right? On this lecture, we have made the central claim that has threaded together through the previous week's lectures. So if we end up proving this theorem, right, I hope that will fully satisfy you that everything we've done so far is mathematically justified, right? There's no cyclic dependencies and such. Okay, so let's just go a little bit further ahead, assuming the policy improvement theorem is okay, and then in part 2 of the lecture we'll actually do a proof of the policy improvement theorem. Okay, at this point maybe you have already seen that there is a natural way to build an algorithm out of this result, right? The policy improvement theorem. So that algorithm, right, or that family of algorithms is called policy iteration. So here's the generic template. Okay, you start with any arbitrary policy pi. You check if pi has an improvable state. If it does, then do policy improvement on pi and get to pi prime. Now pi prime becomes your current policy. Okay, again check if it has improvable states. If it does, again improve. Keep doing this. And at some point you have to terminate, right? That's what we showed on the previous slide, and you will terminate at an optimal policy. See, you might have choice, right, in terms of policy improvement. There's multiple ways in which you might be able to do it. Regardless, right, it follows that you will terminate at an optimal policy which you can return. Okay, so this is policy iteration. So it's helpful to look at a picture, okay, to think about how policy iteration works. So what I have drawn here, let's say, is a graph in which each vertex is a policy, okay, and there is a line connecting two policies. Okay, you'll notice that the lines are all sort of going from bottom to top, right? They're not like properly lateral. There is like a down policy and an up policy, okay, in terms of direction. So let's say there is a line connecting two policies. If from the lower policy you can do policy improvement and go to the upper policy. Okay, so this is a conceptual diagram. It's not really coming from I think a regular MDP, but here's how policy iteration would then work, right? You start with any arbitrary policy. When you do policy evaluation, right, and calculate Q and therefore the improvable set, you will see in general that there are multiple possible improving policies pi prime that you can go to, right? You have the freedom to choose which one. Okay, and so maybe you pick this one. Again, you do policy evaluation, find out what is your improvable states, improving actions. Maybe pick one choice, go to some pi prime. You keep doing this, you're guaranteed to eventually go to a policy that has no improving actions, and that has to be pi star. Okay, so naturally, right, the actual route through this lattice that we take from our starting policy to the optimal policy, by the way, there can be multiple optimal policies, you will reach one of them. Okay, that path is going to depend on how we do policy improvement, right? So how you do policy improvement, or rather how you decide which states to switch, to which actions to switch in the states that you're going to switch, that is called a switching strategy. Okay, so if you have a different switching strategy, you can get a different route, right? Different paths through this lattice to go to the top. Okay, so of course the path depends on it. Also, the number of iterations that policy iteration takes, right, to go to the top depends on it. So it's already somewhat apparent that literally the running time of policy iteration, right, is going to depend on the number of policies visited along this path, right, or which can be thought of as the number of iterations. Each iteration itself, right, remember, is just a polynomial time thing. It's polynomial in the number of states and actions. Okay, all right, good. So this is a policy iteration. What's left still as a unspecified thing, right, is how we are doing the switching. I have said so far there is a lot of choice in how we want to switch states, right? But let's look at a few examples just to get a sense of what is usually done, okay, in practice. So the most common variant of policy iteration is called Howard's policy iteration. Okay, Howard is also the author of some of the early descriptions of policy iteration itself. Okay, and he picked the most natural way of switching states, which is, if you have 5 improvable states, switch all 5 of them. Okay, greedily switch every improvable state. Don't leave any improvable state not switched. Okay. Of course, there is still some choice as to which improving action you will pick. So let's just assume that can be done arbitrarily. Okay. But Howard's policy iteration will switch every improvable state. So here, if there are 5 improvable states, right, you can see that S1 has become green, S2 has become red, S4 has become green, S6 has become red, and S7 has become black. Okay, the other states stay fixed. But this is not the only rule that is applied. Much later, right, in the late 90s, Mansoor and Singh came up with a random policy iteration algorithm where the switching strategy is randomized. Okay, it's not for the same policy pi, the pi prime that you reach, right, will be random. So there's multiple possible pi primes that you will reach with different probabilities. So, for example, from this pi, right, one of the pi primes you could get is what you will get by switching S1, S2, and S7. Okay, leaving out S4 and S6. Okay, so in which action is picked, let's not get into that right now. With some probability will also pick just S4 to switch, okay, not switching S1, S2, S6, S7, or with some probability it will switch all the states, okay. So technically the rule, right, that Mansoor and Singh's random policy iteration applies is if you have 5 improvable states, let's say, right, there are actually 2 to the 5 subsets of this set of size 5. Okay, you can pick all 5 states, or some 4 states, or some 3 states, some 2 states, right, or some 1 state. It's not okay to pick no states, right? If you're not picking any state for improving, then you're going to be stuck at pi itself, right? So there are actually 31 legitimate choices, which is 2 to the 5 minus 1 of states that you can, of subsets of states that you can choose to improve. Okay, so they picked these 31 subsets with equal probability. Okay,